Hello, and welcome to this very brief introduction to Laplace transforms. This presentation outlines the following. An introduction to Laplace transforms. We're going to look at the definition of a Laplace transform, highlight its linearity property, state some reference information we need to be aware of, derive some elementary Laplace functions, look at Laplace transforms standard table that we must get familiar to use, techniques required to simplify functions. This involves trig identities, hyperbolic identities and compound angle formula, and I'll leave you with some tutorial questions at the end of the presentation. Laplace transforms are used to solve differential equations. They're classified as a use of operators, and it's very analogous to logarithms. In level 3 we looked at the use of the laws of logarithms. There are 3 laws, and each of the laws simplifies an arithmetic calculation. For example, the log of a times b, where a and b are numerical values, in log domain can be transformed into the log of a plus a log of b, so a multiplication sum has become an addition sum. The log of a divided by b in the second law can be transformed into log domain as a log of a take away the log of b, so a division has been replaced by a take away operation. And log of a to the power of n, where a and n are numbers, can be simplified into the n times the log of a in log domain. So what's happened is we move from the left to the right hand side of the each law of logarithms. We're actually simplifying the operations. What was a multiplication sum in log domain becomes an addition sum. What was a division sum becomes in log domain a subtraction sum, and what was a power function in log domain becomes a multiplication function. So the principle behind the laws of logs is to make arithmetic operations simpler to do. And the use of Laplace transforms offers a similar process, but it's for solving differential equations. We often talk about the S operator method or Laplace transform method taking us into the S domain, and this S domain is basically taking a differential equation, first or second order, into the Laplace domain and making it into an algebraic equation. So as long as our algebraic skills are a reasonable level, it actually simplifies the process of solving differential equations. As we know, differential equations crop up in electrical or mechanical work and need to be solved. We're only going to look at first and second order differential equations here. We have looked at solving these kind of equations before. We use such techniques as separation of variables and direct integration to solve first order differential equations. There is a method called integrating factor that can be used to solve a first order differential equation, and we also use the d operator method with its complementary functions and particular integrals when we're solving second order differential equations. But what we're going to do now is use Laplace transforms, and we're going to start off by looking at the definition of a Laplace transform, and equation 1 shows you this definition. On the left hand side of the equation, this symbol here is actually symbol eta, it's a Greek symbol. That stands short form for Laplace of a function of t, and the function of t could be t squared, it could be a constant 5, it could be a sine t, it could be a cos t. It's some function that we'll be looking at in our analysis, and we're told from the definition that the Laplace transform of the function of t is defined by e to the st multiplied by the function of t integrated with respect to t between the limits of 0 and infinity, and all Laplace transforms are derived from this definition. We also need to be aware of the linearity property of Laplace transforms. This is no different to what we've come across in our standard integration process. If we have a constant inside an integral, it's literally just factoring up the function of t, that constant can be taken outside the integral. sometimes simplifies the integration process for us. So likewise, if we've got, we're looking for the Laplace transform of k times ft, as the k is just a pure number, that k can be taken outside of the Laplace transform, and we just deal with the Laplace transform of the function of t, and that's what equation 2 is showing us. Equation 3 is almost the same. The only thing that's different here is we have two functions of t. We have a times a function of t here, and b times a function of t here, and all this expression is saying we can take the a outside the Laplace transform and then just deal with the function of t, and we can take the b outside the Laplace transform and just deal with the function of t there. Okay, so linearity is something we can make use of, and it does help simplify the problems. Just as background information, as reference information, we need to be aware of standard derivative tables, standard integral tables. The laws of indices are also used, you'll see in some of the work we're going to do. And there is something called the integration by parts, which you may not have come across before. It's for solving non-standard integrals, and that is used sometimes within a derivation of Laplace transforms. We're going to look very briefly at how Laplace transforms are derived, just to give us an insight into where they come from. And again, we're going back to equation 1, which is repeated here for convenience. In the first example, part A here, our function of t is going to be simply the number 1. Okay, so basically we're replacing this part here of the Laplace definition with simply 1. So e to the minus st times by 1 is e to the minus st, and if I integrate that, that's a standard form. That's like having e to the at, if we look at your integral tables on the previous slide. When we integrate that, that becomes e to the at over a, so in this case it's going to be e to the minus st over minus s, if you follow the pattern through between our limits of 0 and infinity. Just taking the 1 upon minus s outside of the function here, again it's a constant so it can be taken outside, and imposing our limits of 0 and infinity into our expressions, the first term here actually will tend to 0, because don't forget a negative index means it's reciprocal, so that's actually 1 over e to the s infinity, and if you imagine that we're basically dividing 1 by a very, very large number, then that will tend to 0, and in the second limit, when we put in the 0, we've got e to the 0, and anything to the power 0 is going to be 1. So looking at the arithmetic here, we've got minus 1 upon s times by minus 1, that will give us 1 upon s. So the Laplace transform of 1 is 1 upon s. If we now take the function of t to be, instead of being 1, we're going to call it k, which could be any arbitrary number. Again, because it's a linear function, we've got 1 times k here, we can take the k outside and leave ourselves with the 1 inside the Laplace transform. The solution now is exactly the same as part A. The only thing that's different here is the solution for Laplace of k is k upon s and not 1 upon s. Looking at part 3 of this example, the function of t now is going to be e to the at. So now when we look at our definition, we've got e to the minus st multiplied by e to the at within the integral. We can use the law of indices, first law of indices, to bring these two e functions together, so that becomes e to the minus st plus at, and I simply factorized on t here to get to this second stage, and that's really the same as e to the at. It's a standard form where a in this case is the minus s minus a function. So if you follow the standard integral through, you'll end up dividing by the a term, a generic a term I'm talking about here in the e to the at formula, and you'll end up dividing by minus s minus a function. Taken outside of the bracket again, because it's just factoring basically a factor on the equation, I can then put the upper and lower limits into the exponential functions as before. We know the first term in that bracket will go to 0 because we're dividing by a really large number, and the second term, because e to the 0, will be 1. So again, we can formulate a solution. The Laplace transform of e to the at can be written as 1 divided by s minus a. Here we've got a more complicated example of the of a Laplace transform derivation. This is looking at the function of t being cos at this time. I'm not going to go through this in great detail, but when you put cos of at into the definition, you end up with integrated e to the minus st times cos of at. Both terms here are functions of t, so you'll need to use the integration by parts formula, which some of you may have not covered before. Those of you that have, you might be able to follow through the solution for the integration by parts, but as you can see from the notes and these slides, it's quite a lengthy process to end up with the Laplace transform of the cos of at. All we really need to be interested in at this stage is that final solution, that the Laplace transform of cos at is written as s over s squared plus a squared, but the derivation is above. If you want to have a practice at some of these things, solving these Laplace transforms, there's 2 here in exercise 1, sine at and a function of t is equal to t. They follow the same kind of processes as has been shown previously, but I'll leave them with you if you want a bit of fun there. This is what we need to be very careful of using now, and that's the Laplace transform table. All our work from here on in will depend on being able to understand Laplace transforms table. Here we've got the basic Laplace transform table, and later in the series you will see an inverse Laplace transform table as well. But this is the first table we need to be aware of, and I've highlighted in the dark red text here the solutions that we've had on the previous page. So when we had a function of t being unity 1, the Laplace transform was 1 upon s. When the function of t was k, we've shown that the Laplace transform was k upon s. When our function of t was e to the at, the Laplace transform is 1 over s minus a from the derivation, and then the lengthy derivation for cos at that showed us the Laplace transform is s over s squared plus a squared. I've also added in the table an e to the at. I just added this in because sometimes students have trouble with the e to the at expression when the a becomes negative, so I've just added the extra one in there if you want to use that one. And also we've got the sine at function there, which was in the exercise on the previous page. There are more Laplace transforms shown here, functions of t and the Laplace transform. In row 7 here, I'm looking at, we've got the function of t is t, that goes to a Laplace transform of 1 upon s squared. When we look at the function of t being t squared, that goes to 2 factorial, notice that's a factorial, over s cubed, and we've got a more generic t to the n here. And the when the function of t is t to the n, the Laplace transform is n factorial over s to the n plus 1. Don't forget factorials, we've come across them before in our binomial theorem. So factorial 3, for example, would be 3 times 2 times 1. Factorial 4, 4 times 3 times 2 times 1. Other function we've got a hyperbolic function shown. The sine of at is a over s squared minus a squared. We've got the cosh of at, s over s squared minus a squared. Then we've got functions of t multiplied together. The e to the at times by t to the n goes to n factorial over s minus a to the n plus 1. And then we've got e to the at times sine omega t goes to omega over s minus a all squared plus omega squared. We've got the e to the at times cos omega t, that goes to s minus a over s minus a squared plus omega squared. And then we've got the hyperbolic functions here. We've got e to the at times by sine omega t, that goes to omega over s minus a squared minus omega squared, and finally in this table e to the at times cos omega t, and that Laplace transform becomes s minus a over s minus a squared minus omega squared. Okay, we'll be coming back to those in the work we're going to do both in this presentation and in future presentations. Example 2. Referring to table 1 on the previous slide, we're asked to find the Laplace transforms of each of the following a through to d. Let's look at a first of all. So part A, we're asked to find the Laplace transform of 2 multiplied by the sine of t. Now the 2 is just a factor on the sine of t, so I can take the 2 outside the Laplace transform. So on the right hand side of the equation I've written 2 times by the Laplace of sine of t. Now referring to our Laplace transform table, an extract of which is shown below here for convenience, item 5 in the table shows us the function of t sine at. The Laplace transform of sine at is given as a divided by the s squared plus a squared. Now don't forget, in this case there is a 1 in front of the t. We don't write the ones, but it's there. So the a in this case is 1. So now writing the Laplace of sine at, noting that the a is 1 in this case, I would write 1 over s squared plus 1 squared, the a over s squared plus a squared. And of course I'm still multiplying it by the factor of 2. So the Laplace of 2 multiplied by the sine of t can simply be written as 2 divided by s squared plus 1 squared, or s squared plus 1. Example 2, part B, we're asked to find the Laplace of 8 multiplied by the cos of a half of t. I can write that as 8 multiplied by the Laplace of the cos of half of t, because the 8 is a factor on the cos function. Again, referring to the Laplace transform table, an extract of which is shown below here, item 6 shows us the function of t of cos at, the Laplace transform of which is given as s divided by s squared plus a squared. In this particular case, our a is a half by inspection of the original question, the cos half t, cos at, the a is a half. So using the transform below, I can write the cos at as the Laplace transform s divided by s squared plus a squared, in this case as a half squared. So finally, the Laplace of 8 multiplied by the cos of half t is 8s, 8 times s from above, divided by s squared plus a half squared, which is actually a quarter. Example 2 continued, part C. We're asked to find the Laplace transform of a half multiplied by t cubed. Again, the half can come outside of the Laplace transform, so I get a half of Laplace of t cubed on the right hand side. Now from the Laplace transform table, the t cubed is of the form t to the n, item 9 in our table. So the function of t we're using here is t to the n, where n is 1, 2, 3, etc. n is 3 in our particular case. We're told that the Laplace transform of t to the n is n factorial over s to the power of n plus 1. So again, taking a half as a factor, I can write the t cubed as 3 factorial upon s to the 4. 3 factorial, of course, is 3 times 2 times 1, and n in this case is 3. So following the pattern through, I get the n factorial over s to the n plus 1, so that's 3 factorial over s to the 3 plus 1. So now I get a half of 6 over s to the 4. Simplifying that, my Laplace of a half t cubed can be written as 3, that's a half times 6 is 3, divided by s to the 4. Example 2, part D, we're asked to find the Laplace transform of 2 multiplied by e to the 4t. Again, the 2 is a factor on the exponential function, so on the right hand side of the equation I can take it outside the Laplace transform, so I write 2 Laplace of e to the 4t. Referring to our Laplace transform table, the function of t we're looking for here is item 3 in the table, and that's e to the at, where a in this case is 4. So the Laplace transform of e to the at we're given as 1 over s minus a. So in this case we will get 2 multiplied by 1 divided by s, and the a in our case is 4, so that will become minus 4 in this case. So finally, Laplace of 2 multiplied by e to the 4t can be written as 2 divided by s minus 4. If we had an e to the at where a was negative, then we would get 1 upon s plus a, the Laplace transform. Exercise 2, I will leave with you to do. The solutions, the answers are given there on the sheets. There are 4 more functions for you to look at using the Laplace transform table. Okay, going to look at some techniques for simplifying functions that we will need as we progress through this topic area. So the first identities I'm going to look at here are trigonometric identities that are used for simplifying the Laplace transforms. You may have seen these before. These are standard trig identities. Sine 2x can be written as 2 sine x cos x. Cos 2x can be written as cos squared x minus sine squared x. Sine squared x can be written as a half times, open bracket, 1 minus cos 2x, close bracket. Cos squared x can be written as a half, open bracket, 1 plus cos 2x. And also cos squared x plus sine squared x equals to 1. These are all trigonometric identities, some we've seen before in previous work, but they can help simplify some Laplace transforms, as you'll see in a moment. There are also hyperbolic trig identities, very similar in their format, so be careful, they're subtly different. Sine 2x can be written as 2 sine x cos x. Cos 2x can be written as cos squared x minus sine squared x. Sine squared x can be written as a half multiplied by 1 minus cos 2x in brackets there. Cos squared x can be written as a half multiplied by 1 plus cos 2x in brackets, and cos squared x plus sine squared x equals to 1. So those are hyperbolic identities when we're dealing with the sines and the cos's. And finally, we sometimes make use of compound angle formulae. Again, you may have seen these before. In this case, sine of open bracket a plus b, where a and b are numbers, can be written as sine of a times the cos of b plus cos of a times the sine of b. Sine of a minus b can be expanded as sine of a cos of b take away cos of a sine of b. And then for the cos functions, cos of a plus b can be written as cos of a times the cos of b, notice minus sine of a times sine of b, notice the sign change from left to right there. And then finally cos of a minus b can be written as cos of a times cos of b plus sine of a times sine of b. Again, these compound angle formulas can help us simplify some Laplace transform problems. I'm going to show you a couple of examples now where these simplifications are required. In example 3, we're going to look at part A first of all, which says find the Laplace transform of cos squared t. Now, if you look in your Laplace transform table, you won't find the Laplace of cos squared t. It's not given, it's a non-standard form. But if we go to the trig identities, then cos squared, I've used the term x here, variable x, is equal to a half 1 plus cos 2x. So therefore I can write the Laplace transform of cos squared t as equal to the Laplace of a half plus a half cos 2t, following the pattern through for the trig identity. Now we've got Laplace of a half, which is basically Laplace of a constant k, and we know the solution there from the table is k upon s for the Laplace transform, so that's a half upon s, or we can write that as 1 upon 2s, same thing, account for the fraction there. And if we look at the Laplace of a half cos 2t function, again, that's in the tables, that's actually written as s over s squared plus a squared in the table, so in this case it'll be a half times s over s squared plus 2 squared, where the a is 2 in this particular case. If we just simplify that, that becomes s over 2 s squared plus 4. So we can write our Laplace of a half cos 2t as s over 2 open bracket s squared plus 4. Now bringing those two terms together, for the Laplace of cos squared t, we've got 1 upon 2s plus s upon 2s plus 4. So we managed to take the non-standard cos squared t and managed to put it into two Laplace transforms. Sometimes though we simplify them further, as we've done in this case. If I've repeated the line here for convenience, we've got the 1 upon the 2s plus the s upon the 2s squared plus 4. Now we're going to make a common denominator, in other words multiplying the 2s and the 2s squared plus 4 terms together, as I've done on the bottom there. Don't forget we kind of cross multiply here to get the top line. That's basically 1 times 2s 2 open bracket s squared plus 4, and this here is s times 2s, if you think of the cross multiplication approach there. Expanding the bracket on the top, this is basic algebra expansion here. That gives me 2s squared plus 8 plus 2s, and then bringing my like terms together, I get 4s squared plus 8 on the top for my numerator there, over the 4s s squared plus 4 on the bottom, and simply dividing top and bottom by 4, I get s squared plus 2 over s squared plus 4 there. Okay, so the Laplace transform of cos squared t, which is not in our tables, can be written as s squared plus 2 over s open bracket s squared plus 4. Here's we've got a trigonometric identity. Again, this is a sine function, so a very similar approach here for part B. We're now asked to find the Laplace of the sine squared 4x function, and again we don't find a sine squared function in our Laplace table, so it's a non-standard form. So I'm bringing in the trig identity, hyperbolic trig identity here for the sine squared x, which can be written as equals to a half 1 minus cos 2x. Just be careful here. Can you see that the original question asked for a sine squared of 4x, so we must be careful of bringing the 4 inside the sine function here, because our trigonometric identity is just for x, but we actually have 4x. So when we come to expand here, we must put the 4 inside the cos function to get what will be an 8 in the next line. So be careful of that, okay? So now the Laplace of sine squared 4x can be written as the Laplace of a half 1 minus cos 8x, the 4 times 2 giving you the 8, and all I've done on this line is expand that bracket, so a half times 1 gives me the half, and then the half times the cos 8x. Again, going to my Laplace transform table, the Laplace of the first term a half is a standard form. It's k upon s, and the k in this case is a half, so it becomes 1 upon 2s. And then looking in my tables for a half cos 8x, that will use a standard transform of s over s squared minus a squared, and I'm multiplying it by the half here, so it's a half times by the s over s squared plus 8 squared in this particular case. What I've done on the next line is multiplied by the half, and I have it raised the 8 to the power of 2 there to get the 64. Again, bringing the two terms together, we can say that the Laplace of sine squared 4x is 1 upon 2s minus s upon 2s minus 64. Again, if we bring them together with a common denominator, which has been shown here, same procedure as used in part A, we cross multiply on the top, we'll get 2 s squared minus 64 this time, and we'll get s times 2s. Expanding our brackets, we get 2s squared minus 128 minus 2s squared. The 2s squared terms cancel in this case, leave us the minus 128 on the top. On the bottom we've got the 2s times the 2s squared minus 64, so again bring that together, gives me 4s times the s squared minus 64. So minus 128 when I cancel the 2s squared terms on the numerator, and on the bottom line I get 4s open bracket s squared minus 64. All I've done now is divided top and bottom by 4, and I get minus 32 over the s squared minus 64. So my sine squared 4x term can be written as a Laplace transform as minus 32 over s open bracket s squared minus 64. And the final example I've got here is using a compound angle formula. We're given the function of 2 cos omega t plus alpha, and note in the question it says that omega and alpha are constant, so they're just pure numbers. So when we find the Laplace transform of 2 cos omega t plus alpha, the 2 effectively will go outside of the Laplace transform function. Now if you look carefully, the cos omega t plus alpha is actually in the form of cos of a plus b, where a is the omega t and b is the alpha. We are shown from the compound angle formula that the identity can be written as cos of a times the cos of b minus sine of a times the sine of b. So in this case, if we keep the 2 outside of the function, we'll end up with 2 cos omega t plus alpha on the left hand side equates to 2 open bracket, we'll get cos of omega t, that's the a, times by cos of alpha, the alpha is the b, minus the sine omega t, sine of the a, times the sine of the alpha, sine of the b. Okay, all I've done on the next line is just written the in terms of Laplace. It's 2 times the Laplace of the cos omega t plus alpha, so 2 has gone outside the Laplace function, cos omega t cos alpha minus sine omega t sine alpha. Now all I've done on the next line is rewritten it slightly on the right hand side, because don't forget the alpha and omega are constants in this case, so cos of alpha is actually a constant, it's just a pure number. So in the first term here, the cos of alpha can come outside and leave me simply with the Laplace of the cos omega t. And in the second term now and again, the sine of alpha will be the constant. So in the Laplace bracket will just be the sine omega t. Okay. If we look in our standard tables, we will see that the Laplace of sine omega t is a over s squared plus a squared from the Laplace transform table, and if we look for the Laplace of cos omega t in the Laplace transform table, that's s over s squared plus a squared. So now we can write the original function of 2 Laplace of cos omega t plus alpha. We can write that as 2, I'm keeping that outside the bracket for the moment because it's just a factor. We've got the cos alpha, which is the constant, and the Laplace of cos omega t is s divided by s squared plus omega squared, and then that's added to the sine alpha, which is the constant, and that's now multiplied by the omega over the s squared plus omega squared term. Okay, again just rewriting that slightly on the next line, I just like simplified it here. I've got the s times the cos alpha on the numerator for the first term over the s squared plus omega squared, and then I'm adding to that the omega times the sine alpha, just slightly rearranging on the numerator there, over s squared plus omega squared. Notice the denominators of both fractions are the same here, so we can write them over the same fraction. So the final solution here is Laplace of 2 cos omega t plus alpha is 2 open bracket s times by cos alpha plus omega times by sine alpha, and it's all divided by the s squared plus omega squared. Okay, so that's an example of simplifying the Laplace transform using a compound angle formula. Tutorial questions. Question 1 and question 2 wants us to use the standard Laplace transform table to find solutions to part A and B in both cases. Question 3 wants us to find a Laplace transform of 2 parts A and B here, but we have to use a trigonometric identity to solve these problems. Question 4 wants us to find the Laplace transform of a given function, and the hint in the question is to use compound angle formulae. And if you want further fun, question 5 requires us to prove the following Laplace transforms given to us in parts A and B, and again there are some hints in the question to help us to undertake the proofs. Here's the bibliography used to develop the presentation, some very good textbooks I would encourage you to refer to for further information. I hope this has been of use to you, and thank you for viewing.